Welcome, everybody. Today we have our next speaker in the Quantum Computing and Networking series. It's my great pleasure to welcome Don Towsley. I think Don has had a storied career in classical networking, won all possible awards there that there are to be won, including multiple Test of Time awards, Lifetime Achievement Awards from multiple SIGs on networking as well as performance modeling. And the last few years, Don has been focusing on quantum communication. So I thought for somebody who's kind of made the journey, he would be, perfect speaker to come talk to us and teach us more about the exciting problems and what he works on, what made him transition. So I'm really excited that he's here and he could take some time out to chat with us. And with that, I'm gonna let him speak. Thank you, Don.
Okay, thank you, Ratul. I find this to be a really exciting area, so I'm glad to be able to talk about it. As Ratul mentioned, I sort of moved into this area about 4 years ago, and as a result of sort of interacting with a quantum communications person who the two of us were working on a classical networking project, but he kept telling me about all the excitement that there was and exciting problems. And so I'm going to talk a little bit about some of the work that I've been involved with. And actually, Saikat Gua is part of this. I've listed sort of collaborators that work of which I'll be talking about. So I guess the first thing is, why are we interested in this? And the reason is there are a number of applications that it appears would be significantly enabled if we had, let's say, a quantum network. There's been a huge amount of work done on quantum key distribution, but in the end, for it to be useful, it needs to be done sort of across large distances. We know that there's incredible power in quantum computing, like Shor's algorithm, for example, but we also see that these various companies, haven't been able to do much more than build very small, noisy quantum computers. And so that again suggests that maybe what's needed is to sort of connect them and do distributed quantum computing. There's a lot of interest in, let's say, high resolution sensing, let's say, for example, in astronomy, where you have very low signal to noise ratios and you're using observatories and sensors that are scattered around a continent or even around the world. And the sensing can be enhanced tremendously by quantum. And so again, you need some sort of infrastructure to be able to sort of connect these sensors. Clock synchronization is another area. So with that in mind, oops, what's going on? Here's the outline, what I'm going to talk about. I gather you've had a number of people come through and talk about different aspects of quantum computing and quantum networking. I thought about not including any kind of introduction to quantum, but I decided to keep it in because it's been my experience from my past and also from teaching that it's useful to sort of be exposed to it a number of times. So I have a short Quantum 101 overview. Then I'll say a little bit about challenges in quantum networking, and then I'll talk about some of the work that I've been involved in having to do with routing path selection and sort of modeling quantum switches.
I think we just gotta thank you for including the introduction. Like we decided, sure. I think it's useful to, yeah.
Right. And it's interesting, I'm not quantum trained, and it sounds like you've had some speakers that are quantum trained, and you'll get sort of different introductions to it. So, we're comfortable with the classical computing world. We have bits they take only two values, 0 or 1. They're physically represented by a two-state device. The canonical example is a light bulb being off or on, but it could be some kind of a circuit where you have two voltage levels, and depending on the voltage level, you interpret it as either a 0 or a 1. In the quantum world, you have quantum bits, referred to as qubits, and they are two-state quantum mechanical system, and there are a number of them in nature. The one that I always keep coming back to is a photon, and that the state has to do with the polarization. And so I have here sort of two polarizations, one in the horizontal plane, the other in the vertical plane. And you could think of them as sort of representing two different states. And so typically the horizontally polarized photon would be thought of as being in the 0 state, and using, let's say, the bracket notation, it's referred to as ket 0. You can think of it as a column vector, 1, 0. And then the vertically polarized photon is in the ket 1 state. And you can think of it, it's a column vector 0, 1. Okay, but that's not the end of the story, because the photon, of course, can be polarized at essentially any angle. And so you have what is referred to as a superposition of states. It's a combination of the 0 state and the 1 state. And so a general state, ket phi, would just be this linear combination of the 0 and 1 states, with alpha and beta as the coefficients. Alpha and beta are complex numbers, and the constraint is that if you square them and you add them up, they sum to 1. It's a sort of a normalization constraint. So what that means is that you can have, let's say, this polarized photon, and it can occupy any one of an uncountable number of states. Okay, and it's interesting, if you take, let's say, this photon in this superposition state right here, and you pass it through a beam splitter, what will happen is that the horizontal polarized will go up, vertically will go across. When it's in a superposition, either one of them can take place, but it's either or and not both. And this quantum, this qubit then has been converted from the superposition to either the qubit 0 or qubit 1. And this constitutes a measurement. And what will happen is, if you, let's say, prepare the state over and over and over again, and repeatedly do this measurement, what you can do is learn something about the superposition coefficients. The probability that you'll measure a 0, that it'll go up, will be equal to alpha squared, and the probability that you measure a 1 will be beta squared. Okay. Now, we've talked about a single qubit, but you can have a 2-qubit state. Going back to the single qubit, you can think of the state 0 and 1 as being basis states, because you can write any superposition state as a combination of them. With a 2-qubit state, you have 4 basis states corresponding to the different combinations of 0 and 1 for the qubits. And a superposition state, let's say with 2 qubits, then would be expressed like this right here. Okay. Now I want to introduce this notion of entanglement, and the definition is pretty straightforward. Two qubits are considered to be entangled when you cannot describe the state of one of them independent of the other. Okay. And I'll just mention, because we're going to be working with these throughout the talk, there's a two-qubit state referred to as the Bell state, which is an entangled state that looks like what I've written down here. It's the combination of 0, 0, and 1, 1 with the coefficient 1 over root 2. And this is an important resource for quantum communication, actually for quantum computing. So let's look at this Bell state. And let's suppose that what we do is we give the first qubit to Alice and the second qubit to Bob. And so now I've just expressed it sort of in that way. This is Alice's qubit, and then this is Bob's qubit. The 0, 0 can be expressed as you'll see it expressed as a tensor product of the two states 0, 0. Okay, and suppose now that Alice measures her qubit, okay, and it can be either 0 or 1, and what will happen is when she does the measurement, she'll either generate a 0 or a 1. If she generates a 0, then when Bob measures his qubit, he will generate a 0 as well. Likewise, if she measures a 1, then Bob will measure a 1. Okay, and I've sort of showed this according to this diagram right here. And one of the nice things about this is that the probability that, let's say, Alice generates a 0 or a 1, each of them is 1/2. And so this is, in principle, a way that Alice and Bob can generate shared randomness across distances. And certainly, there are quantum key distribution protocols that take advantage of this. And this is a basis of a lot of quantum communications, computing, as I said, quantum key distribution. Okay, so I talked about Alice and Bob, and they could be, let's say, some distance apart. Suppose that Alice has a 2-qubit state, and what she wants to do is to transmit the second qubit to Bob. And it could be this Bell state, for example. Okay, and so she might have, let's say, an optical fiber connection. So she'll send, and there's a good chance it will get lost. She could prepare another state and try again, and she could keep preparing and preparing, and eventually Bob will get, let's say, the second qubit. And the probability of success, let's say in this fiber, is given by essentially E the minus alpha L, where L is the length of the fiber. And the important thing about this is that this probability of success decays exponentially with distance. And as I understand, with classical communication, it decays much more slowly than that. I think is like a power law. And so that limits how far apart Alice and Bob can be. And so the idea was generated that what you ought to do is, let's say, introduce what's called a quantum repeater.
Don, can I ask a question on the previous slide? Just for those of us who are kind of, classically trained, like what exactly is decaying here? Is it like this? I mean, is it like the strength of the signal? Is it like, you're losing kind of phase distortion is happening?
Right. So yeah. I guess two things can happen. And I'm not an expert. One, of course, is the photon could just get lost. It could disappear. What is really most likely going to happen is the photon is going to interact with the environment. And so when it interacts with the environment, then its state, its quantum state just degrades, and in sort of in the extreme case, it actually goes back to that there's no information in it. And as I understand, with quantum information, it's incredibly fragile. It's challenging to protect it from degrading with respect to the environment. So, for example, what might happen, let's say if this had been that Alice had a Bell state and she was sending the second qubit to Bob, in the extreme case, what will happen is that Bob will have a quantum state that'll be independent of Alice's. You'll no longer have entanglement.
Okay, thanks.
Okay, so the idea is to introduce sort of what's called a quantum repeater in the middle. And then the way that this system would operate is that it's in two phases. First of all, each of the links would generate a Bell state. So let's say in this case, between Alice and the repeater and Bob and the repeater. And once that was done, then it would perform an operation called the Bell state measurement that would essentially propagate that entanglement, those two entanglements into one between Alice and Bob. And I'm not going to be going into this, but if you have a bunch of memories at this state, then what you can do is, maybe Alice and the repeater successfully create their Bell state at some point, and so it stores the qubit there. And then as soon as Bob creates its Bell state, then they can do the measurement and propagate it. And that has the effect that it sort of makes the probability of success look as if, let's say, the distance has been halved. This wouldn't happen. You can only get this effect when you have memory at the quantum repeater. That's important to note. And one thing about this is that the repeater won't know, what the state is of the superposition. And so now you can think of like creating a line of these repeaters, let's say between Alice and Bob, and the behavior would be similar. Each of the links generates a Bell state, and then you do a Bell state measurement at each of the repeaters. And if everything succeeds, then you propagate the entanglement so that it's between Alice and Bob. Okay, and so this can be used then to connect the two of them. Now, it's possible that something will fail, and in that case, you will still get sort of an exponential decay, but not like you do without the repeaters. Here we're looking at, again, the rate in logarithmic scale as a function of a number of hops or between Alice and Bob. Okay. Now, why is this useful? Well, it turns out that these entanglements can be used to allow Alice to transmit quantum information to Bob. So suppose Alice wants to send a qubit that it has prepared to Bob, and it has an end-to-end entanglement with Bob. Then what it can do is it can combine that with what's referred to as teleportation to do the transfer. And I'll just walk you through an animation of that. So here we have Alice and Bob. Alice has, let's say, a qubit in some superposition state. We have a repeater in the middle. First thing is we generate these link level entanglements. Then we do a Bell state measurement, and if it succeeds, then what we'll have is an end-to-end entanglement between Alice and Bob. And what Alice now does is she essentially entangles the qubit that she wants to transmit or teleport to Bob with her end of the Bell pair, do a measurement, and that's going to generate, if you recall, when you do these measurements, you always generate essentially classical information, ones and zeros. That'll, let's say in this case, it generates a 1, 0, and Alice then sends this over a classical network to Bob. And Bob, in the meantime, he has no idea what the qubit is that Alice wants to send. But he can use these 2 bits to make a correction and essentially transform his qubit, that what used to be the other end of the Bell pair, into the state that Alice wanted to send. Okay, any questions? Okay, so now let's look at a network. What we'll do is it's going to be a collection of quantum switches that are going to be connected via lossy links. These switches are going to host quantum memories. And think of it, the only difference between a switch and a repeater is that this switch is going to have the flexibility to decide which links to perform Bell state measurements on. Okay, and so what the way that this network will operate is you'll take pairs of quantum memories in adjacent switches, and you'll try to form Bell states between them, and some of them will succeed. And then at the second step, you do measurements between the memories where you were able to generate these Bell states. And in doing so, you end up connecting the Bell states. And so the result then would be, let's say, an end-to-end entanglement here. Okay. You do Bell state measurement on these 3 switches. Okay. Just for your information, these end-to-end entanglements, these end-to-end Bell states, it's referred to as an E bit, E standing for entanglement. So here are the kinds of challenges that come up. I think there's one sort of fundamental question, and that is, what's the right service to provide? I've been describing this network as if what it's doing is it's essentially generating end-to-end entanglement in the form of Bell states between pairs of nodes. Another way that you could, a service that you could have this network provide is it could just do direct quantum information transfer. If Alice had, let's say, a quantum state that it wanted to transmit to Bob, that what it would do is it would just, let's say the network would select a path between Alice and Bob, and it would then just, a network would be responsible for transferring that state across to Bob. I'm not really going to talk about that. That turns out to be equivalent to an entanglement distribution network, because we've seen how you can transfer quantum state using teleportation if you have entanglement. And clearly, if you can directly transfer quantum information, then you could always transfer the second qubit of an entanglement from Alice to Bob. And so they're equivalent. But the entanglement distribution network seems to be more interesting intellectually to sort of study. Okay, so then you have sort of standard questions that arise in classical networks. You know, how do you allocate resources? How do you share among multiple users? Routing, you know, how do you select paths? Performance modeling is also an interesting question. You know, what's the capacity of the network? Can you say something about what the latencies are going to be? You have a measure of the quality of the quantum state that you also have to worry about. That's referred to as fidelity. So that's also a something to be considered. And then typically what hasn't been considered by, let's say, the people, the researchers, certainly in the physics community, is, you know, what should the control plane look like? And you know, and so it seems like you might want classical control on quantum data plane. And there are questions about, should they share the same substrate, or should they be completely separate networks? And so there's some interesting questions there. And then, you know, measurement and management.
I had a question.
Yeah, go ahead.
So you have this bullet point, direct quantum information transfer. And so one thing I was trying to understand is, if Alice can't really choose the state of an unobserved qubit, then how can she transmit state to Bob?
So let me go back. I want to make sure that I understand the context. So we're talking about, let's say in this case, with teleportation. In the case of teleportation, Alice doesn't have to know anything about the state that she's transferring. And what will happen is that in the end, Bob will have a qubit that's in that state. That doesn't mean that Bob knows what it is, although Bob can perform a measurement, but in doing the measurement, he's going to destroy the state and essentially get a classical bit out of it.
I guess what I'm trying to understand is, like, are you describing this as information or transferring information?
Yes. So you could think of it as the following. Alice has an apparatus for generating a qubit in a particular state. Okay, and maybe and it comes from, let's say, doing some sort of quantum computation, and she just wants to pass it on to Bob.
Can I ask a question also?
Yeah.
So is there three-way entanglement? I mean, I've heard of these Greenberger
right.
states. I'm not sure if that's three-way. And then would that create new capabilities for networking?
Yes. Let me defer that to later, because I'm going to introduce it when I talk about routing and path selection. And I probably won't answer all questions that you have, but you'll at least see some of the capability that it provides you. Okay, so what I'd like to do is talk about some work that I did. Actually, there are going to be two pieces of it over the last couple of years with my colleague SciCAD and with a number of grad students on routing and path selection. Okay, and I think that we're going to look at it in the context of a 2D grid. I think that comes from the fact that much of this has been driven by physicists, and they love lattices, but the ideas are transferable to sort of a more general network. I think it turns out it's easier for us to sort of make sense of what's going on here. We have a 2D grid. Alice and Bob reside, let's say, in these different locations in the grid. The links are probabilistic. By that, the links can generate Bell states, but there's a probability that it will that may fail. And so we could think about, how should Alice and Bob connect themselves to each other, so, let's say, to generate an end-to-end entanglement. And what we could do is we could just look at the shortest repeater chain. This would be an example of it. And here, P is the probability that the link is able to generate a Bell state successfully. And if we do that, then basically it looks exactly like the linear chain that I showed you before. And so the performance curve essentially looks like this, logarithm of the rate as a function of the number of hops separating Alice and Bob. And it turns out that we can do much better than that. Okay, so if you recall, the way that this network works is in the first step, all the links attempt to generate Bell state. And so let's say that this is what it looks like after that. And if you notice, Alice does have a connection to Bob. Okay. And the role of let's say the repeater or the switch then is to try to connect Alice and Bob. Okay, and of course it can't hold on to the entanglement long, and it needs to be able to make whatever decisions as efficiently as possible and using as little information about the state of the network. And the simplest routing operation is really that a switch could perform a Bell state measurement, or now I'm referring to it as an entanglement swap between two of the links. Okay, and if it does it properly, then it's going to end up generating an end-to-end entanglement between Alice and Bob. So question is, how might one of these switches make decisions just using local information? You could imagine, if we come back to this, if we create these link states and we then ask all of the switches to broadcast to everyone else, which links made it and which didn't, then of course you could in principle figure out what path connects Alice and Bob. But the problem is that it would take the latency in sort of propagating that state information would be too much. Okay, so the question is, how can we do it using local knowledge? And we'll focus on U, and I'm showing it's for neighbors, and Alice and Bob are situated in these locations. Okay, well, if after the first step only one of the links succeeds, then we're done. We can't do it. You can't do anything. If two links come up, then there's only one choice for you, and it should just go ahead and do a Bell state measurement between those two links. Of course, that doesn't mean that there's going to be success in propagating it to Alice and Bob unless somehow, you have sort of a string of successes from W to Bob and V to Alice. So suppose that three links come up, and Mihir Pant, the student who was involved in this, came up with the idea of using sort of a distance routing algorithm, where what you would do is maintain for Alice and Bob the distances that each of its neighbors were from those two parties. Okay, this neighbor here is 3.2. I think he was using Euclidean distance, a distance of 3.2 from Alice and a distance of 2.2 from Bob. And then what you would do was to pick the two links that if everything was successful, would result in sort of the shortest path between Alice and Bob. And in this case, it turns out that that corresponds to connecting V and W. If you have 4 links up, then again, you do the same thing. You first of all figure out which two neighbors, let's say, will give you the shortest path. I think in this case, it turns out that if everything works out, V and W are the best. And then you just go ahead and do the measurement between the other two links. Okay, so this is just a simple heuristic that's using the only information that's using is knowing the distances of the neighbors between from Alice and Bob, and just which links have come up. And so the question is, how well does a local rule like this do? And so here I'm showing the rate in logarithmic scale as a function of the number of hops between Alice and Bob. And I have this blue curve corresponds to the rate that you get using multipath routing with global information. And global information is really just again, a heuristic. It's, suppose that all the switches know the states of all of the links, then it's just applying a greedy shortest path algorithm. Okay. The red curve corresponds to what you get using the local information. It's a multipath routing algorithm because it is possible that you might generate multiple paths or entanglements between Alice and Bob simultaneously. And then the yellow curve is if you just took the shortest path between Alice and Bob and you just relied on that. And so, for example, if you have two users that are separated by 10 repeaters, it turns out that the multipath routing with the local information, it increases the generation rate by a factor of 100. So that's for the case where you have a single flow. We started to look at what you might do when you have multiple flows, and we just looked at where you had two flows and left it at that. But suppose you have two Alice-Bob pairs, and one thing that you could do, the baseline would be that you just time division multiplex all of the resources between the two pairs. Okay, in which case, at any time step, one pair gets the entire network. And if you do, we're looking at the rates of the two pairs, and this line essentially corresponds to a time multiplexed. You could do the following, it sort of makes sense looking at the way that the pairs are separated, is just give all of the resources on the left-hand side to the pair 1 and the resources on the right-hand side to pair 2. And in that case, what you get is this multi-flow spatial division sort of capacity region. And in this case, it turns out that you can get much, much larger entanglement rates for the two pairs than if you were to just sort of time multiplex. I guess I have a red line here, and that's interesting. It corresponds to the case where you're still doing time multiplexing between the two pairs, but it turns out that there are situations where, although the resources have been given to Alice, let's say pair one, a switch can tell that it can't possibly help that pair. And so it makes a decision to try to help the second pair. And in doing that, you can do slightly better than just standard time sharing. Okay, so one of the problems here is that with this, certainly with this local rule, it's easy to see, come up with examples where things could go bad. Here I have Alice and Bob, and I have sort of a configuration with all of the successful link level Bell states have been created. And this switch right here, it turns out that using the local rule, it will do the measurement between these two links. But we can see that there's actually a path like that. And if it had only done a measurement between these two, that would have succeeded in generating an entanglement between Alice and Bob. And so here, it turns out it's useful to go beyond Bell states. And so the question was asked about GHZ states. So, right, yeah, and n-partite or n-GHZ state, you can think of as sort of just a generalization of a Bell state, where it's a superposition of these two states right here. You know, the 0 state for all n qubits and the 1 state for all n qubits. And I'm going to show you how it helps in our context, but of course it turns out it's useful for lots of other applications.
Don, just kind of curiosity, in this day and age of SDNs and centralized control, why are you and your team seeking local distributed algorithms? Like, why not just have the control plane be just centrally configured? Or
oh, okay. Well, I have a couple of things to say about that. Let me go. Let's say in this case that you know that of course you need to propagate information like which time steps does pair 1 get the resources, which time steps pair 2, and you're going to need a control plane for that. And so you can think of it that or which spatial resources do you assign to each of the pairs, and you need a control plane for that. But in addition, you can give a little bit of local autonomy to the switches, because they may be able to make a different decision that will help. That's one answer. The other is, to be honest, I think that what you're going to want to do is something like circuit switching, or let's say maybe burst switching, to deal with the fact you have all of this randomness. And that's all going to be sort of controlled using SDN, and let's say with a central control plane. But intellectually, this is more interesting to look at this point.
That I buy. What are the timescales of these decisions?
These decisions could be on the order of like microseconds.
Okay. So that could be a pragmatic reason then to try.
Right. So certainly locally, if you want to do things really dynamically, you have to use local. But as I said, I think what you're going to probably do is you're going to say, okay, you have lots of Alice Bob pairs, and what you're going to do is going to say, well, Alice and Bob, this one gets this path, some fraction of time, and other Alice Bob pairs get other things, and then you'll have like let's say SDN and the central controller sort of implementing these decisions. Okay, so coming back to this, what you could do then is I had sort of presented these decisions or algorithms for, let's say, generating end-to-end entanglement using Bell states and Bell state measurements. But you could do, in this case, where you had 3 successfully generated link entanglements, you could do a 3-way GHZ measurement. And if you recall, this is the example where the local rule that I presented fails. But if you do a GHZ measurement, then you will get a connection between Alice and Bob. And actually what I'm going to show is it turns out that you get distance independent entanglement generation rate by doing this. Okay, you don't have an exponential decay. And it turns out sort of like mathematically, this sort of transforms to a percolation problem, which has been well studied in physics. And so let me just give you a sense of what happened. So we're going to look at 2 protocols. One that does 3 GHZ measurements. It measures up to 3 entangled links. If all 4 links have been entangled, it just selects 3 randomly. And then a second one that measures up to 4 entangled links. And what we're looking at here is the y-axis is the link success probability P. The x-axis is the measurement success probability Q. And we're interested in the regions where we will get good performance. Okay, so when P and Q are small, performance is going to be bad. And it turns out that according to percolation theory, you get something that's referred to as a subcritical region. And you can think of it in the context, in our context, is that you'll never generate long distance connectivity. If Alice and Bob are pretty far apart, they're rarely going to be connected. But you have sort of a boundary. If you're doing 3 GHZ projections, this is the boundary right here in yellow. And if your success probabilities lie inside this region, then you have a probability of having long distance connectivity. This is for 3 GHZ. The 4 GHZ protocol has sort of a larger region where you have connectivity. And I'll show you what the implications are. This is the graph that I showed you before. And what we're going to do is we're going to take points in each of these regions. And if it's in, let's say, where the success probabilities are not very high, this subcritical region, then as the distance between the consumers grows, the rate that you get is essentially 0. If you're in this supercritical region where the probabilities are large, then what's going to happen is no matter what the distance is between the consumers, you're going to get essentially a constant rate. It doesn't depend on the distance. And then I have a point here, this green one, and it's sort of illustrating that you have sort of like an exponentially decaying rate, but it eventually goes to 0.
What's the unit of distance there?
This is hops, number of hops.
Okay.
And in this grid, the assumption is that geographic distances are the same between neighboring nodes.
So is it that the 3-way entanglement allows you to kind of branch in 3 directions simultaneously?
Right, exactly.
Well, related question is, how do planning algorithms, and graph search algorithms map onto this? I mean, is this basically that you have this parallel capability to simultaneously pursue multiple paths?
If you want, you can think of it that it's right. All of this is being done concurrently. It's like the switches look, they see what links have, let's say, bell states, and then they do these measurements. And the nice thing in the quantum world is that everything commutes, and so it doesn't matter what order things actually take place. And so you can just do it in parallel. Okay, I'm going to talk about another piece of work looking at the performance of quantum switch. Here, just tell you a quantum switch will have a bunch of memories. And it'll have interfaces, and you can load the memories from, let's say, qubits coming across the interfaces, or you can read out the memories onto the interfaces. You have the capability of doing measurements. They could be, let's say, 3-qubit, n-qubit measurement. You have some quantum logic that you can use to operate on, let's say, the qubits held in quantum memories, entanglement, photon entanglement sources, and then, of course, classical computing and communications. And what we did was to look at sort of like the simplest question on what the capacity of a switch might be. And what we did was we looked at the case where you have, let's say, k users, and you're serving bell states to all pairs of users. Okay, and the way that you do it is you generate these link level bell states, and then you do measurements between the various link level bell states to propagate it. We assume that the bell states are generated according to a Poisson process with rate μL for link L. The switch can store B qubits, and the success probability for a bell state measurement is Q. And if the links are all identical, it turns out you can model it using a very simple Berth-Teth Markov chain. And the capacity that comes out of it in the case of infinite amount of memory is given by this expression right here, which is really very intuitive. Each request requires, think of it, 2 resources, and that explains the 2 in the denominator. The rate at which you're generating link level bell states is mu times the number of links, k. And then, of course, only a fraction of them succeed in generating end-to-end entanglement Q. Expression for the expected number of stored qubits. It's given in terms of the number of links, and if you have lots of links, it's essentially, on average, you store one half of a qubit. We looked at link heterogeneity, and I'm not going to give any analytical results, but it turned out, from our perspective, it was sort of cute because you get sort of an interesting sort of star-like Markov chain, but it turns out to be very easy to sort of solve. Here's an example with 3 links, what the capacity might look like as a function of, let's say, the buffer size. And what we have is we have 1 link that's almost twice as fast at generating bell states as the other 2. And when you have infinite memory, you get this rate of 1.95. And in red, we're showing the effect that having finite memory has. And here, as I said, one link is nearly twice as fast as the other two. And what the memory is really being used is it's storing qubits that have been generated by the fast link, waiting for, let's say, the other links to generate Bell states to do measurements on. And there's some effect of, let's say, the amount of memory on performance. We looked at a case where you're generating n-GHZ states, n-partite GHZ states, in the case of a homogeneous system, and you get, again, a very intuitive expression for the capacity. Again, you're generating link level Bell states at rate mu k, and you can only use a fraction of them, q, and then, of course, you need n to generate a complete GHZ state, and an expression for mean memory. I'll point out that, I mean, the expressions are intuitive, but it turned out that it was challenging to prove this. Something else we've looked at in the context is, suppose that you want to serve both bipartite and tripartite state. And one way that you could do that is you could just time division multiplex the switch between the two services. And if you do, here I'm showing the capacity, the rate at which you can generate Bell states, and on the x-axis, the 3 GHZ states. And if you do multiplexing, that corresponds to these dashed lines. I think the blue one is when you only have one memory per link. In the red, you have two memories per link. And the question that we asked was, could we do better than multiplexing? And so the answer was yes, that you could devise randomized policies that achieved these sort of solid lines, which are a bit better than the time multiplexing. So that's sort of what we've been doing. To summarize, entanglement distribution service is really very different from data transfer service. I think much more interesting from perspective of a networking research. There are new problems that quantum network introduce, and in some cases old problems, but with interesting wrinkles. And at least we've been, the focus has been on, performance, on doing resource allocation. We've been looking at how you generate, distribute, and manage entangled state in noisy environments. We have not been looking, but an important question is really what the control architecture should look like. And then, how would you do management? And I'll just say that, the research is in its infancy, and with lots of exciting problems, that it's going to have, I think, a life that, if you have PhDs coming out, they'll easily be able to do interesting and fun things for the next 10 years. Okay, and that's it.
Thank you. So I got thinking about this, like, how do you view this performance modeling work? Like, in the sense of, I'm assuming hardware does not exist, so you cannot go back and validate the model. So your hope is that this modeling work informs future engineering, or like, how do you see it kind of fitting into this assumption? Like, typically when we build models, like, I think you kind of go validate and get like a simplistic version of reality in some way. In this case, the reality doesn't exist, or I don't know when
right.
Yeah.
So there are two things that we're doing. There's several simulators that have been developed. We're using one that came out of TU Delft. It's called NetSquid, and it has built into it let's say, sort of models of the behavior of a number of different devices. So we've been, one of my postdocs has been sort of extended the capacity model to look at where you have workload of requests, and he's derived, some interesting results, but we're validating it with the simulator. I guess the other thing that we expect to do, because of this center of quantum networking that at the University of Arizona, we're going to have a test bed that we'll be able to try things out. And what I expect is, we'll develop resource allocation algorithms and we're going to try them on the test bed. And I think they're going to be looking to us for guidance on, how do you do scheduling, how do you do path selection, and so on and so forth. And we'll be able to compare against what our models say.
Got it. That's kind of cool. All right.
Yeah.
I have a question.
Sure.
Is this susceptible at all to man-in-the-middle attacks? Because there's like these nodes in between Alice and Bob.
We haven't really looked at what would happen if you have some adversary that's trying to mess up, let's say, the generation of entanglement. I'm sure there's a lot that they can do just because of the fact that this is so fragile. Having said that, the one thing that quantum is really nice about is that you can detect, let's say, man-in-the-middle kind of attacks. And so then, although, so at least you could detect it and then decide what you should do as a countermeasure. And the reason is that, if this adversary is playing around with your entanglement, either it lets the entanglement take place, or if it manipulates it, it's going to destroy it. And so that'll be noticeable by Alice and Bob. It's sort of how QKD works.
Okay.
The question is, when I'm thinking about these routing algorithms that you're talking about, they definitely remind me of planning algorithms like you'd see in robotics, where you could look at depth first search or breadth first search or A star. And I guess the question is, is that analogy correct, and have all the sensible algorithms been evaluated for this application? If so.
Okay, so I'm not familiar with the search algorithms, specific search algorithms you're talking about. I think in the case where you have, let's say, a single Alice and Bob pair, I think you're right. That really you're trying to explore, and you can do it simultaneously. It's like the entire network as a way of like generating these paths. In the case where you have multiple users, I think it's going to be probably going to end up being quite different. I think that's where I think you're going to probably want to borrow ideas from circuit switching and burst switching. That you'll want to set up sort of paths that'll last for a while to be used. And I don't know if that shows up in the robotics.
Okay. Yeah, just two quick comments. I mean, in robotics, they're typically assuming that the computer can only look sequentially, so that makes it a little bit different.
Yeah, I know you have another comment. Something that took me a long time to appreciate. The person who was teaching me this always presented this as sequential, and I kept thinking that it was completely a sequential process of setting up these sort of entanglements and doing the measurements. And it's not. That's one of the nice things about quantum, is you can do it all at once and you don't have to worry about the timing between the different operations. Go ahead, you had a second comment?
Oh, the other thing I was going to say is that, when people in robotics are looking at planning algorithms, they sort of have two categories. One is, point to point, and then, but some of the algorithms are any to any. So those any to any ones would seem to be more relevant for this problem.
Yeah, we'll have to look at it, and certainly there have been a couple of sort of follow-on works, from on our work, and I think there's a lot to be done. And so if you have any good ideas, try it out.
Again, thanks a lot.